Hello, dear students. I hope all of you are fine. And today I'll be discussing Compton Effect with you. And before having a discussion on Compton Effect, all of you know that COVID-19 has been changing its morphological structure. In certain formats it's very dangerous, in certain formats it's less dangerous, but my suggestion to all of you is that we should follow the guidelines that are time to time given by the government, and we should make sure that the virus that's out there, probably right now there's a variant of COVID-19 which is probably known as Omicron variant. It seems it's not that much dangerous, but still we should follow strictly the SOPs in all formats, and we should make sure that we should not become the carriers of this virus, and we should follow all formulations. So we should follow all the tactics, all precautionary measures that are out there to make sure that this virus does not spread. Now, coming to our discussion, I would like to talk about Compton Effect today. In my previous lecture, I talked about photoelectric effect, which probably is a confirmation of particle nature of light, and a further confirmation of particle nature of light, I mean that light is made of photons, is Compton Effect. Compton performed an experiment in 1992. He performed this experiment to measure the distribution of scattered radiations from a target material on which the radiations are allowed to fall. So the point here is that if you have a target material in which you have electrons, and if radiations, highly energetic radiations, probably in this case X-ray radiations, are allowed to fall on a target material, and assuming that light is a wave, we expect certain outcomes of that state of scattering that will take place. When the radiation falls on the target, if it's a wave, certainly there will be transformation of energy from the radiations to the electrons in that material. If we assume that the electrons in that material are momentarily at rest, so what we expect is that these electrons should vibrate, they should oscillate. In other words, I should say they should accelerate. So when the radiation is allowed to fall on the material, the electrons will absorb that energy, and then this energy will be re-radiated by these electrons. Keeping in view that what's going to happen is that if you assume that light is a wave, it's a radiation, it's having a wave nature. So what we expect is that the scattered radiation must have the same frequency, or it must have the same wavelength as that of the incident radiation. So when we allow the radiations to fall on the target, what happens is that the scattering takes place, and we expect that there should be a process of absorption of the energy, and then there should be the process of emission of that energy. And the whole process should take place in such a way that if you are detecting this radiation, with the help of a detector, it must have the same wavelength as that of the incident radiations. So this is the idea. The idea is that that we expect that this kind of thing should happen under these circumstances. So in this case, A.H. Compton, he performed an experiment, and he expected the same thing, that what I was revealing you, expected that there should be symmetrical radiations should come out, or the radiations that will be detected, they must have the same wavelength. So you can see that there's a crude diagram of Compton effect. In this experiment, a radiator is used of molybdenum. It's an X-ray source. The highly energetic radiations are produced. Then probably a filter is used, because we want the radiations of some particular wavelength that we should allow to hit the target. So for that purpose, a filter is used here, and then there is a scattering substance. I mean, the radiations that probably the K alpha line radiations of molybdenum, which are filtered out from this filter, they are allowed to fall on this scattering substance, which is made of carbon. And then there is a movable detector, you can say, it's a spectrometer, who can detect the scattered radiations that will come out of it. So what were the observations of this experiment? And what is expected, as I told you before, it was expected that the frequency of the scattered radiations must not change. Their wavelengths must not change, on account of assuming that these radiations are behaving like waves. So the point is that you have the radiations, X-ray radiations coming out of molybdenum source. They are filtered out from this filter, and then probably you collimate that radiation into K alpha molybdenum, and then they hit the target, and then you have the scattered radiation. Probably the right thing here is that this radiation is hitting the electrons in this material, and you are expecting that you will detect all the scattered radiations, and all of these scattered radiations must have same wavelength, or must have the same frequency as that of incident radiations. And to the surprise, the result of this experiment was not consistent with the wave theory of radiations. It was not consistent with wave theory of light. So what was observed in this experiment is that by moving this detector, you were able to detect the radiations that are scattered from this scattering substance. And it was observed that there were two components of frequencies that were detected by the spectrometer. And one of the components of the frequencies have the frequency less than that of the incident radiations. And we call them as modified radiations, or incoherent radiations, scattered radiations that have been scattered when the radiations have fallen on this scattering substance. They have been scattered, and what we have obtained is unmodified radiations and modified radiations. So modified radiations are those whose frequencies are found to be less than that of frequencies of incident radiation, and unmodified radiations are those in which there is no change in the frequency of the incident radiations. So probably the outcome of this experiment is that the scattering is taking place, and we are expecting that the scattered radiations must have same frequency all along this detector that's moved in all directions. But to the surprise, what was obtained was that there was presence of frequencies having less frequencies, less energies than that of incident radiations. So this outcome of this experiment was explained by Compton himself, and he used the idea of Max Planck. He used the idea of using the idea of Max Planck is in itself an explanation that if you're explaining certain things in an experiment by assuming that the radiations that are falling on the target, they are photons, that means you are treating them as particles, you are treating them as blurred balls, or simply I should say you are treating them as balls. So this is what Compton did. What Compton did, he assumed that the light falling on the radiations, probably X-ray radiations, falling on this target is made of photons, quantas, packets of energies, and with this in mind, that the radiation that's falling out on this target is quantized, Compton came out with a mathematical conclusion where he obtained that there is probably the shift in wavelength, there is shift in frequency, I should say. That shift is by virtue of the assumption that the radiations that are falling on this target are quantized in nature. So what was the outcome of Compton's experiment? The outcome of the Compton's experiment is that the radiations that are falling on the electrons, which are probably assumed to be free and momentarily at rest, the scattered radiations have both the frequencies in them. They have the frequencies equivalent as that of the incident radiations, and they have the frequencies which are less than that of the frequency of the incident radiations. So in order to explain what Compton did, he came up with two fundamental postulates. He came up with two fundamental assumptions. And what were these assumptions? The first assumption was that we treat that the radiation that is hitting the electron must be treated as a quantum of energy. It must be treated as a photon. It must be treated as a ball. And the collision, when this ball will hit the electron as a target, the collision between the photon and the electron must be elastic. So by saying elastic, that means the energy and momentum of the collision must be conserved. So the very first thing is that the collision between the photon and the electron is elastic collision. And the second important thing that's here is that the electron is probably treated to be at rest. So electron will behave as a target. You can see this diagram. You have a photon, and this photon is going to hit this electron, which is momentarily assumed to be at rest. So when this photon will move towards this electron, it will have some energy. So what will be that energy? That energy, in accordance with the Max Planck, E is equal to h nu, and it will have a momentum, and that momentum will be h nu by c. Now when this photon will hit the electron, which is assumed to be momentarily at rest, there will be transfer of energy. there will be transfer of energy. What will happen to the photon? It will be scattered in this direction, and the electron will move in this direction in a two-dimensional plane. And if it moves in this direction, we call this electron as a recoil electron. And you can probably yourself say that now this scattered photon must have some energy. That energy, it must have some frequency. That frequency is assumed to be nu dash. You can resolve the components, and you will have a vertical component and you will have a horizontal component. So vertical component in this case will be h nu dash by c sine phi for momentum, and it will be h nu dash by c cos phi for momentum. Okay, so for the electron, the same story goes here, that this electron is going in this direction. It's making a recoil angle theta, and it certainly will have the components. You can resolve these components as mv cos theta in horizontal direction and mv sine theta in the vertical direction. I think the things are clear about this diagram. If I would like to repeat it, you have an incident photon treated to be a particle, treated to be a photon, having some energy, and hitting an electron, and after hitting an electron, the photon has recoil energy. That energy is, the photon goes in this direction, and assuming that electron goes in this direction, and making certain angles with respect to the horizontal. So resolving the components of momentum, in this case, we have resolved, you can resolve the momentum for the scattered photon, and you can resolve the momentum for the recoil electron. So moving on, keeping in view the very fundamental assumptions of A.H. Compton, the very first assumption that the collisions must be elastic. So collisions must be elastic means there must be conservation of energy before and after the collision, and there must be the conservation of momentum before and after the collision. So in view of these two assumptions, and keeping in view the diagram that we have discussed, we would like to write an equation for conservation of energy. So for conservation of energy, it will be the energy of photon plus the rest mass energy of electron. Then it will be the energy of the scattered photon, and then you will have the energy of the recoil electron. So you can see the symbols have their usual meanings. All of you are very well aware about them. H is Planck's constant, nu is the frequency of the photon, m0 is the rest mass of electron, c is the speed of light, which is constant, and nu dash is it's the frequency of the scattered photon, the photon that is scattered after hitting the electron, which is assumed to be momentarily at rest. The moment there is a collision between the photon and the electron, the photon, you have a scattered photon going in this direction, and you have a recoil electron going in other direction in a two-dimensional plane. So this equation will hold for the conservation of energy. And the next equation here is that you have conservation of momentum. So conservation of momentum, certainly it's a two-dimensional plane, so the momentum must be conserved along x component, and it must also be conserved along y component. So what we have done here, we have written down the conservation of momentum for this process along x. So this is conservation of momentum along x. So that will be h nu by c plus, because your electron is momentarily assumed to be at rest, it will have zero momentum before the collision. So this will be your momentum of the recoil photon, and this will be the momentum of the recoil electron. The same story will go for the y component of this process. You can see that before the collision, there's no motion along the y-axis. Therefore, this this must be 0, then h nu dash by c sine phi minus mv sine theta. So probably we are here with three important equations. The first equation is conservation of energy in this collision process. Then the other two equations involve the conservation of momentum. And this is the conservation of momentum along the x-axis, this equation, and the next equation is the conservation of momentum along y-axis. Okay, so we have written down those equations, those mathematical equations that were very much the demand of the situation. When there is a collision between a photon and an electron, which is assumed to be momentarily at rest and free inside the target. On manipulating these equations, the equation of conservation of energy, the equations of momentum, conservation of momentum, when we simplify these equations, we boil down these equations to the final result, which is a Compton shift, and the final result is lambda d dash minus lambda is h by m naught c, 1 minus cos phi. Where you can see the left hand side of this equation is giving us the measure of the shift in the wavelength. That means what was experimentally observed, what was experimentally obtained as a result of some experiment is confirmed here by this equation, because I'm not getting lambda dash minus lambda is 0. I'm getting lambda dash minus lambda is dependent on phi. It's dependent on angle of scattering. It depends on angle of scattering. It does not depend on any other quantity in this equation, because the rest of the things that appear in this equation, you have a Planck's constant, you have rest mass, and you have speed of light. All of these are constants. So from this equation, we can measure the shift, how much shift there is in terms of the wavelength. So if we take a special case of this equation for the sake of an argument, we say that if phi is 0, that means if the angle of scattering is 0, that means this phi is 0. In that case, delta lambda is 0. So delta lambda 0 means there is no scattering at all. The scattering will not take place. The scattering will not take place because if we treat phi equal to 0. Now, if we treat phi equal to pi by 2, in this case, we can put up the value of phi and we can measure the shift in the wavelength of the radiation that has been detected by the detector or a spectrometer. Now, what we have assumed in this, what was assumed by Compton in this situation is that you have an electron, assuming this electron to be free and assuming this electron to be momentarily at rest, you are expecting the frequencies coming out of it which are less than that of the frequencies of the incident radiations. And we call such frequencies, we call such scattered frequencies as modified frequencies or modified radiations. Now, if in actual situation, we go in an actual situation where electron is tightly bound in an atom, where it's not free, what the assumptions that we have assumed for the time being, if we quit the assumption that electron is not free, it's not free, and if it's not free, then the target will not be the electron in that case. The target will be the whole atom. The whole atom will be hit by the photon. And all of you know that the mass of this atom is infinite with respect to the mass of an electron. So if that is the case, that's why I have written down the Compton equation here. Again, lambda dash minus lambda is equal to h by capital M. This capital M is a symbol that is telling us that it is the mass of an atom. mass of an atom. Mass of an atom. So the photon, the radiation that's hitting the target is not hitting an electron, it is hitting the whole atom. And this mass is very, very large. It is infinite with respect to the mass of an electron. If that is the case, in that case, probably you will not observe any kind of Compton shift. You will not observe any kind of the measurement of this shift will be extremely small. It will be that much small that it cannot be measured in this case. Therefore, in this case, I will say that the Compton shift is practically zero. There is no Compton shift, and this will go to the radiations that have been detected by the spectrometer, whose frequencies are same as that of the incident radiations. So there is no shift in the wavelengths of the photons that have been hitting these atoms. So wherever they are hitting the free electrons, you have the Compton shift. Wherever they are hitting the atoms as a whole, there you will have unmodified radiations. The frequency of the radiated radiation, scattered radiation, will be same as that of the frequency of the incident radiation. I hope you will at least get the feel of this experiment, feel of this theoretical explanation that's given to the collision process between the photons and electrons. So with this, I would like to thank you all for bearing with me and getting certain ideas which you feel are comfortable for you. Thank you.